What specific problem do you address with the Alias-Free Latent Diffusion Model, AFLDM, and why is shift-equivariance crucial for tasks like video editing and image-to-image translation?
The Alias-Free Latent Diffusion Model, AFLDM, specifically addresses the instability and inconsistency in image generation caused by aliasing effects in traditional latent diffusion models, LDMs. This instability manifests as significant variations in generated images, even with minor perturbations, such as pixel shifts or flow warping, which can lead to flickering in video frames and inconsistent outputs in image-to-image translation tasks. Shift-equivariance is crucial for tasks like video editing and image-to-image translation because it ensures that small shifts in the input lead to proportional shifts in the output, maintaining temporal coherence and consistency across frames. By implementing an equivariance loss and a modified self-attention mechanism, AFLDM enhances shift equivariance, thereby improving the stability and quality of generated images and videos. This capability is particularly beneficial for applications requiring high stability and consistency, such as video editing and normal estimation, where coherent results are essential.
Can you break down the technical steps involved in the proposed AFLDM method, particularly focusing on the role of the equivariance loss and how it is integrated into the training process?
The proposed alias-free latent diffusion model, AFLDM, incorporates several technical steps to enhance shift equivariance, primarily through the integration of an equivariance loss into the training process. First, the equivariance loss is defined to optimize the error between the outputs of shifted inputs and the corresponding shifted outputs, ensuring that the model adheres to the principles of fractional shift equivariance. This loss is added to the original training loss of both the variational autoencoder, VAE, and the U-net, effectively reducing aliasing effects during training. Specifically for the VAE, the loss is computed separately for the encoder and decoder, while for the U-net, it is applied to the denoising process, ensuring that the model maintains high shift equivariance throughout the generation pipeline. Additionally, the equivariance loss is complemented by anti-aliasing designs in the network architecture, which together help to constrain the bandwidth of the continuous latent representation, thereby enhancing the overall stability and consistency of the generated outputs.
Provide a simple example that illustrates how the equivariance loss functions in practice. For instance, how would you compute the equivariance loss for a shifted input image?
To compute the equivariance loss for a shifted input image, we first define the input image, x, and apply a shift operator, t_delta, to it, resulting in a shifted image, t_delta, x. The equivariance loss is then calculated by comparing the output of the model on the shifted input with the expected output after applying the same shift to the model's output. Specifically, for a model, f, that rescales the inputs by a factor, k, the equivariance loss, L, is computed as \opening square bracket L equals ft_delta, x t_k c dot delta, fx, _2 to the power of 2. This loss function quantifies the difference between the model's output for the shifted input and the output that would be expected if the model were truly shift equivariant. By minimizing this loss during training, the model learns to produce consistent outputs under shifts, thereby enhancing its shift equivariance. For instance, if delta is a shift of 1 pixel, the loss would ensure that the output for t_delta x aligns with the output for x shifted by the corresponding rescaled amount, k.
What quantitative results or metrics do you provide in the paper to demonstrate the effectiveness of AFLDM compared to existing LDMs? How do you ensure these results validate the shift equivariance property?
In the paper, we provide quantitative results using metrics such as shift-PSNR, SPSNR, to evaluate the shift equivariance of the alias-free latent diffusion model, AFLDM, compared to existing LDMs. The SPSNR is calculated for both the encoder and decoder of the VAE, as well as for the LDM during the denoising process, allowing us to assess the consistency of outputs under input shifts. Our experiments show that while standard LDMs exhibit severe quality degradation in fractional shift results, AFLDM maintains higher SPSNR across denoising steps, demonstrating its robustness to input shifts. Additionally, we validate the effectiveness of AFLDM in generating consistent results for video editing and image-to-image tasks, where the alias-free design significantly reduces flickering and enhances stability. The incorporation of equivariance loss during training further ensures that the model optimally learns to preserve shift equivariance, as evidenced by the improved SPSNR metrics.
What limitations did you discover while developing AFLDM? Are there specific types of image or video inputs where this method might not perform as well?
While developing the Alias-Free Latent Diffusion Model, AFLDM, we identified several limitations primarily related to aliasing effects and the inherent instability of the generation process. Specifically, we found that even with the implementation of anti-aliasing modules, aliasing amplification could still occur during training, particularly due to the processing of boundary pixels and nonlinearities, which can lead to degraded shift equivariance over time. Additionally, the iterative denoising process in LDMs can cause aliasing to accumulate across steps, further complicating the generation of consistent outputs. Our experiments also revealed that self-attention operations in the U-net are sensitive to global translations and not inherently shift equivariant, which can affect performance under irregular shifts. Consequently, while AFLDM demonstrates robustness for many tasks, it may struggle with inputs that involve significant irregular pixel shifts or complex deformations, such as those encountered in highly dynamic video sequences or images with intricate textures.
What future research directions do you propose based on the findings of your work? Are there specific modifications or enhancements you believe could further improve the method?
Based on the findings of our work, future research directions could focus on further enhancing the shift equivariance of latent diffusion models, LDMs, by exploring additional anti-aliasing techniques beyond those implemented in our alias-free latent diffusion model, AFLDM. Specifically, investigating more advanced filtering methods or adaptive sampling strategies could help mitigate aliasing effects even further. Additionally, the integration of more sophisticated self-attention mechanisms that maintain equivariance under various transformations could be beneficial, potentially leading to improved performance in tasks requiring high temporal coherence, such as video editing. Another promising direction is to explore the application of AFLDM principles to other generative models, such as GANs, to assess whether similar improvements in stability and consistency can be achieved. Lastly, conducting extensive evaluations on diverse datasets could provide insights into the generalizability of AFLDM across different image-to-image translation tasks, further solidifying its applicability in real-world scenarios.